when it runs through the motor, the current signal that is caused by this voltage should also be free of harmonics and clean. But of course, in practice, what you are going to see here, Deron, please go to the next one. What you're going to see here is some harmonics on your current waveform here. As you can see, with the voltage supplied at 50 hertz or 60 hertz in the United States, you have some harmonics at third and fifth here. And of course, that could be different depending on the condition of the equipment. However, what is clear here is that if these harmonics that you're seeing, or these waveform distortions that you're seeing on the current waveform, are not present on the supply voltage, that means, what that tells you is that then these must have come from the mechanical behavior of the system. Now by analyzing these distortions and the root causes, you can actually find mechanical faults. So, and that is really the basics of this technology. And as you can see here, if you have two identical motors with the same condition, with the same supply voltage, you will have the same level of current waveform distortions. And then what the EMCM does here is it creates the digital twin and it replicates the motor itself and has the same level of current outputs at, of course, different operational conditions of the motor. Now, imagine that after, of course, we are going to elaborate more on that learning or digital creation period later on, which is taking approximately 10 to 12 days. But imagine that the scenario where a motor has been learned, a digital twin has been created, and you have now these on the second graphic here, down here, on where it says current 2, you have these harmonics. So first of all, what the system does, it looks at those waveform distortions and signals and compares them with the proprietary database that Artesis has created in the past 20 years. So that's really important because that gives the EMCM system the ability to detect the existing faults on the system. So, and if you learn an equipment which has already some issues, and if you do not detect those, then pretty much the system will be useless. So, and then later on, after this initial fault detections or the existing fault detections, now what's going to happen here is, of course, the system will monitor the critical assets 24/7. Now, down the road, 2 months later, 6 months later, let's say, some of these mechanical components on the motor or driven equipment starts to deteriorate. Now, what's going to happen here is that you will see additional basically harmonics or distortions on the current waveform. Darren, can you click next? No, can you go back? Just we want to see these additional, yeah. So as you can see here, these on the current waveform 1, you see these additional harmonics, and they are still not present on the supply voltage. So they have come from the additional mechanical deterioration of, either bearings or unbalance or misalignment, you name it. So what they do here, they cause additional distortions. And since the system is constantly comparing these actual measurements with the one that it has created, and it takes a difference between the two, and that gives us this residual current waveform spectrum. Basically, we amplify this and analyze it in a power spectral density and on a frequency domain. So if you see here, you have some amplified harmonics, and based on the frequency of these harmonics and the magnitudes, now we can easily tell what sort of mechanical problems that we are seeing here. To give you an example, if you were to have an imbalance, you would see a one-time RPM peaks plus and minus or around the line frequency. If it was 60 hertz, let's say, on an 1800 RPM system, you would see a peak on the 30 hertz, a peak at 90 hertz. That will tell you that this is an imbalance issue on the system. Just this was one example. Now, imagine another scenario where you have these harmonics on your supply voltage. Darren, can you click next? So what's going to happen here is, it wasn't this slide, but okay. If you were to have harmonics on your electric supply voltage, basically, then both EMCM and the motor will have the same distortions, and that means this is not a mechanical issue, but an electrical one. So this system can distinguish between an electrical and mechanical problem. Furthermore, of course, since the system creates a cause and effect relation, so it looks at the process variations because it learns how the system behaves under different conditions. This might be because of different products that it works on any given day of the week or time of the day. So certain processes have been learned, but once you have something new or an unexpected or unintentional, the system will be able to detect that and giving you the notification that you have a process change. Could be a process issue or operational problem, or it may be an intentional change. And once, if that's the case, and if it's confirmed, you can update the system, which then will learn that additional condition introduced to the system. Darren, can you click next? So now one big question here that we get a lot is that how the system is capable of seeing mechanical issues with the electrical signal, and the answer to that question is shown here. Basically, there is an air gap between the rotor and stator in any electrical motor, which has, in theory, of course, a uniform electromagnetic field, which is distorted whenever you have a mechanical issue, whether you have a bearing problem, whether you have an unbalanced misalignment or broken rotor bar or stutter issues. All of these mechanical problems will basically shift the air gap between the rotor and stutter and causing dynamic or static eccentricity, which in turn, of course, distort the current waveform and creating these harmonics or distortions on the current waveform. So basically, this is how the system is seeing these mechanical problems or even electrical ones by these air gap distortions because of any kind of problem, whether it's on the motor or the drivetrain or the driven equipment, will be propagated into this air gap. And then, of course, depending on the severity, you will have higher amplitudes distortions. And if it's not so high, then you will see medium level or low level of distortions. And that gives us the ability to determine the severity of the problems. And next there. So as I touched early on, that the system takes 10 to 12 days to learn a system. And the reason for that here is that it's trying to maximize to its coverage of motor's operational conditions, right? So again, it has to learn the more different load levels, different motor speeds, and the gain of the system. Basically, then it creates clusters for all of these conditions. So each time a cluster is created, it is created for a certain condition of the equipment. When it's in monitor mode, then the results or the measurements are compared with the closest cluster to that operational profile. So this is really important. That increases the resolution of the system and also accuracy of the system. And furthermore, through this cluster creation, the system can actually detect process changes. And once it's verified with an update, additional clusters will be created for the new condition introduced into the system. So that's the reason it takes 10 to 12 days. For stable applications, these 10, 12 days can be adjusted to a shorter time, or if it takes longer, it can be extended. So, however, 10 to 12 days is a pretty standard value for us, and that's how long it takes. And right after that, you will have results available for existing faults. And then, of course, in the monitor mode, it will continue to monitor and compare with these clusters. Next, please, Darren. Yeah, here just a detailed look of the learn period, we call it, and same thing for digital twin creation. So, and this is important because you keep a lot of machine learning algorithms and AI here and there all over the industry. But what's actually really happening here is that, first of all, this is not a statistical approach as with these other machine learning technologies where you would need a lot of data for a long time, right? So we're talking about months or years in some cases. Here, again, we keep it in 10 days. And what this 3 to 7 days means in more technical terms here is that this EMCM system is taking three-phase voltage, three-phase current at 2.5 kilohertz sampling rate for every 1.5 minutes. And that's called iteration. So, and it here we take 4,000 iteration for learn and another 8,000 for improve, and the combination of both, once it's completed, the system will go into monitor mode, basically to monitor the system together with the existing false information. So, and that's really, I think, a significant advantage of the system. Within that small period of time, it can actually learn how the system behaves and then have an initial baseline for further monitoring, of course, throughout the future. So this is pretty much how the system works. Maybe at the end, if there are questions about this, I can try answer. But now I'm gonna hand it over back to Deron. Thank you.
Thank you, Tumay. Yeah, you certainly explain it much better than I could have. So thank you for that. Okay, so again, so now you hopefully get a little bit more insight into how the system works. So this is again, the system and what it looks like. It's a very compact system. It goes right into your MCC panel. It's only about 3.8 inches long or tall, however you want to look at it, because the bottom here is DIN rail mountable. You could leave it loose in the MCC bucket, but you can also, you get a DIN rail mount at the bottom. So it's 3 3/4 inches wide and then just about 2.5 inches deep. So very compact. And this is just about the same. This is your local display. It's optional. It doesn't require it's not required to install it, but it's nice to have a local display in the MCC room there. If you're walking through, any alarms will be, you'll see the status light up here flashing red. And also all of the information that we're monitoring is available through the menus and scrolling through the different screens. So it is nice, but again, it's not required for the system to work. Okay, so very compact, easy to install system, and it's very powerful, of course. So it does provide, just all the different factors that you need in a fantastic condition monitoring system: early fault detection, comprehensive fault coverage, energy efficiency effects of that fault, the triple E number, power monitoring. This is also a fantastic solution where other technologies can't even get to submersed pumps and borehole pumps, anything that's intrinsically safe. And then, of course, everybody's trying to get into more remote monitoring with COVID world that we lived in today. You can set these up one time and you can look at the data from anywhere in the world. And then, of course, the last part here, automated fault diagnosis. That is, the system is doing, most of the work for you. Occasionally, you can do some advanced analysis, but 80-90% of those faults are automatically detected and reported to you. So, what does the software look like? We have two versions of it, an on-premise software and also a cloud version of it. So on the top here, we're looking at the manager's view of a number of machines, and then the bottom, is the same thing on the on-premise software. So, the manager he or she may not care if I have a bad bearing, the plant's got a rotor problem. Is my plant running good today? He or she, that's all they care about, Then they'll start, hammering the maintenance teams and the reliability teams. Why do I see so much red here? So just to get a quick overview of how the plant is running, we have this multi-tiered software platform. And then there's multiple tabs in here, like the electrical parameters. We can look at that. And then under the summary, it'll list all of those faults with that EEE number. So we can see, geez, we got 20 faults and it's costing us, I don't know, another 200,000 kilowatt hours, per 12-month period. So you can see, how efficient your whole plant is running. So that's, the upper level software. And then this is the real powerful page. This is the on-premise software. So we can now start drilling down into what those faults are when it does show you red in the overview page. So we look at the bar graphs here. We have a few in caution. The light blue bar graph on the left is what it saw during that learn period that Tumay just explained. We get that initial learn period. So that's, we don't really have a baseline because that baseline is already known for that particular motor in our model base of millions of motor signatures, and that's that green line that we have here. But we want to know, where did we start when we first started monitoring, and where are we currently? So if I look at this stator, the internal electrical, maybe there's some insulation degradation going on there. So it's starting to climb up. We're still in the white, good area, but why? So occasionally it's good to look at these, even though everything's in the monitor mode. There's nothing, in alarm. But this caution, there's just a lot of information here, but it's simplified. And you can even set your own thresholds. Say, this has been, nice and even with where we started, and now it's starting to go up. Maybe we want to change a threshold and say, okay, before I even get to the caution, just let me know if this thing is continuing to climb so I don't have to go in and look at it every day. And here is that the EEE number again, which is just a, it's a fantastic feature of this whole system, because you can really start to quantify, how much all these faults are really costing the plant. And then, of course, we have the power metering and usage, running hours, all of that is tracked as well. Now, we mentioned a few times that you can look at some PSDs. This is our, if you have any vibration guys on here, the spectrum for vibration. We have our similar spectrum. It's called the PSD, the power spectral density, and you can enter in bearing information, gearbox, belt ratios, and do some advanced analysis. And but I'd like to add that later because, again, most of the faults are automatically detected, but sometimes you want to dive a little bit deeper into these faults, and Artesis does provide training on how to do this analysis. We have a whole trending page, which is also very powerful. The bar graphs that I showed in the previous slide, that's the rolling average of 3 days of data. So those bar graphs will creep up slowly because we capture things so early. We don't want to give a lot of false alarms. But if you see that trend going up, that bar graph going up, now we can look at the trend of that particular fault. Maybe it's a bearing, and just we get a data point every 15 minutes that we're plotting. So now we get a lot more data for that trend, and we can look at the data a little bit more. frequently and see if it is continuing to rise on a daily basis, and maybe it might trigger some maintenance action on that particular machine. So here's the on-premise software version of that trending, and the PSD. What's hidden here on the right-hand side is where you can enter in, select the bearings and plot out the fault frequencies for each particular bearing, so you can find out if it's the, inboard motor bearing or the, the pump outboard bearing, inner race, outer race, so you can get more detailed with this spectrum analysis. But again, for the majority of your faults, the software is doing everything for you. Okay, so as we've both mentioned, we can monitor a wide range of anything, any type of equipment that's being driven by, a three-phase AC motor. So we have pumps, fans, conveyors, chillers, mixers, air handlers, compressors, all of that data fed through the EMCM or EPCM if it's a generator. And it goes to the server. From there, we can, again, send the data to third-party software, to the your local HMI, send it to the cloud and to the web IoT software that we provide. And you can view that, of course, from anywhere. Here's a few screenshots from the cloud-based software. The web IoT gives you this, different type of view for your overview of your plant. On the main page, you see the top 3 energy users. Any faults that are present will be evident here, and then we have some daily, hourly, daily, and monthly energy consumption that's hidden behind this window. And then for each particular machine, we have all of your phase balances, your three phases, voltage, current, quick trends here. There's a separate trend, just like I showed you on the previous slide. So both softwares, give you just a wealth of information. So this system, of course, can be applied to, the shipping industry, anything that's really remote, because we can also tie it into a 4G router and send the data out, through, cell modem, through anywhere in the world, up to the cloud and to the web IoT Artesis portal. So you can monitor, wind turbines that may not have communication local, as long as there's some type of cell signal somewhere, we can send the data out that way. Right out of the device here, we do send the data out initially from the EMCM via Cat6 Ethernet cable. So you can tie that into your local switch, get it into your local network. And with the cybersecurity these days, some companies are just, we don't want cloud at all, and we can just cut off this the WWO part of this and keep it all on your local network, because the data, again, which is unique, I think, in these days, it doesn't have to go out to the Artesis cloud or have somebody at Artesis looking at the data for you. It's all done within the software, so it doesn't really require an internet connection at all. But some other companies do want everything on their cloud, so that's the only time you would ever need an internet connection, is if you're going to use the web IoT, the portal. So of course you need internet for that, but again, you don't need the internet for the data to be analyzed. It's all done within the software. So this is just a quick recap of all the different things that we do. We detect those faults. We give you the instant diagnosis and assessment. We give you these corrective actions and work order information. So we don't just say, hey, you have a fault, and we don't just say, hey, you have a fault, it's a bearing, but we also give you some recommended maintenance corrective actions and the severity of it, so you can kind of, hey, I need to get this thing fixed in the next month, the next 3 months, next 6 months. Everything has just a lot of detailed data here. Okay, the comprehensive fault types and alarms. This is not a complete list, but it touches on just a lot of things that no other system, I don't think, one single system can do the way that Artesis does. Mechanical faults, so misalignment. We have unbalance or imbalance. Structural looseness, bearing issues of the motor and driven side or gearbox, belt driven equipment, those types of issues. Gearbox again. Where did I put gearbox in? And of course your electrical issues, rotor, stator, short circuits, windings, loose external connections, insulation degradation, and basically all of the different types of things that you'll get. Short circuits, winding slackness, and then the process. This is another unique thing I think to what we do is the process-related faults. So it could be leaking valves, it could be plugged filters, it could be cavitation in a pump. All done with one system, and irregular airflow and maybe a compressor. And again, those are all, you can't list everything that we can find there because there's just multiple, just so many different driven equipment that a three-phase AC motor is driving. So it'll learn those particular processes and then be able to flag all kinds of different process-related faults. Okay. Now, again, we mentioned before, this is a fantastic solution for, ATEX zones, any intrinsically safe areas, explosion-proof areas. So in addition to, all of your critical assets, but if you have, some maybe something that's not so critical, but you do want to monitor it, and it's in a explosion-proof area, it could just be a fan or whatever, cryogenic pumps, borehole pumps, cooling tower fans. So this is a fantastic solution for just anything that's hard to reach, or just, maybe other technologies, you're getting the same technology, but it costs twice as much to get it ATEX rated. This always going into the MCC panel. You can see an installation here of a customer. And next I'll touch on the installation itself. So right off the shelf, you could have these up and running. And, I've had it, showing up on site with a pilot project, running the data to a laptop, and had it up and running in an hour, actually less than an hour. So we just need to get the voltage, we need to get the current, and then the data out, right? So the arrow pointing towards the orange terminal block here, the 3 voltage leads with the, it's just a 12 or 14 gauge wire. So again, right off the shelf, very easy to install, Then we need the current. Down here, we provide you with the correct sized CTs. You don't have to source those. We have them for you. And these are custom made for Artesis and this application. So we provide you with this cable here with these 3 plastic clips, and each one of the CTs are clamp-on CTs. So you don't have to remove these big heavy cables and possibly cause a fault, by not tightening them correctly or whatever. We just simply clamp them on. There's an arrow on them, point it towards the load. Common question is if there's a VFD. Yes, we can monitor, VFD-driven equipment. We put it on the load side and not the line side. So on the load side for anything that's in that cabinet, arrow pointing towards load, and we provide you with about 6 feet of cable there, so you have plenty of room, to install the CTs. So now we have the voltage, the current, and then it's just communication out. The power supply is 120 volt from the cabinet. So again, very simple to install, and very little planning to get them implemented. Okay, so we have a couple of case studies here. I'm going to jump out of here and show you, let's see, let me get into, I'll make sure so this is a good example of a customer up in Maine that had an external electrical fault. They didn't know what that meant. They asked me because they're just trying to keep their plant running. So this external electrical fault looks like it was pretty loose before. This is the trending page, but let me go back and just show you, the bar graph. We were running good, everything was fine, and then the bar graph, jumped up. It was climbing up over time, and then it finally went really high, went into full alarm. He thought he had fixed it, and then we looked at the trend again and said, just there's got to be something else. And then he finally the next week called and said, found the smoking gun. very loose connection. I believe the local disconnect, and then you can see the bar graph went right back down. So really nice example of a external electrical fault. Now here's same plant, different machine, and this is a mechanical fault, a misalignment. So they took this skid here. Sorry, let me back up. They took this whole skid and they moved it. They picked it up with a forklift and moved it to optimize the flow of the wood chips. This is a new facility, so they're still tweaking the whole operation. But they lost the alignment. They never thought of checking the alignment after moving it, because again, they're just trying to keep the plant running. So we saw that spike in the bar graph for alignment. If we look at the trend with the power consumption, trending up when we had that misalignment. And here we plotted the bearing parameters along with that misalignment. So again, you can see the stresses that are now being put onto the bearings. So this is a really nice case study to show all the different things that we're monitoring and the effects of just a simple misalignment that could have easily been avoided. So I helped them out. I took my Rotaline and went up there and helped them realign it. And then you can see all the trends came right back down. And there we are, running back smooth again. So let me jump out and get back to our PowerPoint. And we have a few more case studies. I think Tumay might jump back in here and explain this one.
Okay, thank you, Deron. So this case study here we have is an example of gearbox fault detection right after the learn period. This was an automotive plant down in Mississippi. So here what we had was, of course, the user was already suspecting that they had some gearbox issue, and they installed this system as a trial onto the same conveyor system. And again, within 10 days of learning period, the system was detected that the gearbox issue was on caution level. And when analyzing the spectrum, we gave them more advanced analysis that directing them into where in the gearbox they had the issue, which they also verified by using vibration analysis. And in fact, they have put this out on LinkedIn and shared it as a case study as well. And I think on the next slide there, and we have the confirmation with vibration analysis. And in fact, that was the case with the gearbox. So, and of course, again, this is important as a case study to show that this system is able to detect existing issues. And of course, when that gearbox even deteriorates further, then that second bar graph will go up and then show the user that it's getting actually more severe. And maybe they should plan and maintenance to address the issue. And of course, another thing here was if that conveyor system, it was actually a 20 kilowatt conveyor motor, but nonetheless, if it were to fail, the whole production on trim section would stop and they would lose $250,000 an hour. So that's really, it's not only the size of the motor that must be taken into consideration when monitoring these systems. It's the effects of any shutdown, any failure on this system on the whole production is also a significant one. So that was the case here.
Mm-hmm.
So the next case, Darren, we have, if you go to the next one.
Yeah, this is the one that I just showed a
That's the
video
one
on.
you already used, so we can skip this one
I was
and then
thinking
go.
and we do have a few more case studies, but it's an hour long. I just want to save some time to try to open it up for questions in case anybody has questions.
I think that's better because we've covered enough case studies. Yeah, it's like
Okay, so we do have 5 minutes left. We can stay on longer afterwards if people need to stay on. But yeah, we'll open it up to questions to myself or Tumay.
sure. Okay.
So if you want, just go ahead and.
Deron, this is Jim.
Yeah, hi Jim.
Yeah, I just want to verify that you have this recorded. A lot of information, and I'm not as well. I'd like to review that. So, how would I go back getting to the recording?
I can send everybody that joined here, or anybody that wants it a recording of this. So just I'll make sure I'll make a note here to get that to you, Jim.
Please, thank you very much.
Sure. Andrew too, looks like. Yeah. Any other questions?
Yeah, Deron, how you
Yes.
doing today?
Good. How are you?
Good. So the training, the advanced training for understanding the frequency spectrums, how do we access that?
Tumay? So I know they are.
Now we're planning to offer training webinars starting from next year. So, and of course, we can also plan individual online or even face-to-face training sessions for users who wants it. So, and of course, the documentation of those trainings will be shared. So you can also study if you like. But we will have frequent training webinars moving forward in next year.
Okay, and then the other question is the AMT Pro. Is the interface with the cloud on the horizon? Is it coming? Is it there?
It's almost there. I think we kind of need another month or so to complete that, and probably launched in December or at the very latest next year. So,
And all of the information that I have already in the AMT Pro will then be available via a cloud platform, correct? I won't lose anything, right?
no, you won't lose anything. In fact, there's a next version of the software on the local AMT Pro, which will take backup of the data in case you encounter some problems. So we will push that back, the update into the devices. But in any case, you won't lose it. And once the web is available, you can send everything into cloud without losing any data.
Okay, thank you.
Sure.
Okay. Any other questions?
Okay, what if machine has a fault on day one or develops fault during the learn period? So this is a good question, which we were trying to touch on. If the machine has a fault on day one, the system will detect it because again, every finding it has or the model it creates is also compared to this proprietary database that we have, which detects the existing faults. And if that fault starts to develop during the learn period, which is again 10 days, it's going to be learned. And also, if you take into consideration that the pace of a development fault would be actually months in many cases, so it will not affect the ability of the system to detect the developing faults or existing faults on the system. Is there any electrical speed limitation for? Yes, it's actually 20 from 20 hertz to 120 hertz. So that's the range that it operates. Anything slower or faster, it's a speed limitation for us. How often? The RPM is basically whatever those frequencies would equal to. So, if it's a two-pole motor or four-pole motor, the RPM numbers will change. That's why I wanted to answer with frequency, actually. But if you translate that into 1800 RPM system, I think and 20 hertz would be equal to 600 RPM. On the motor side, 10,000 RPM motor is just too high. So no, it's yeah. Usually the upper limit would be 4,020 RPM. And would I max? How often are measurements made? And I think we also answered this, but just to repeat that again, every 1.5 minutes, the system takes in data at 2.5 kilohertz from the 6-channel 3-phase voltage and 3-phase current. And how much of it stored is optional. At default, every 10 hours, the spectrum data is stored into database, SQL database. And the trend data is every 15 minutes, but you can make it every 1 minute if you like. So that depends of you, but usually the default values are very optimal in order to keep the store's database size at an optimum level. Would Fmax frequency be different? No, the Fmax would still be right now. It's going to be 1250, whether it's 60 hertz or 50 hertz. But we have plans to increase this sampling rate to 10 kilohertz. Then Fmax will be 5 kilohertz, regardless of the motor speed or frequency.
Okay. And
So, any other questions?
okay, I think we're good. Yeah, thanks again, Tumay, for helping
Sure.
out and staying late tonight. I know it's late on a Friday for you. I appreciate that very much. And thanks to
Okay.
everybody for their time today. I do have a list of folks that have asked for the recording. I'll once that's available, I will get that over to you. And please, feel free to reach out to us if you want to know who your local representative is, and anything else that you need. Feel free to reach out to us anytime. So thanks again. And
Hey, Deron,
yeah,
you've got one extra question there, how to separate unbalanced from alignment.
Oh, okay. All right. Yeah.
Thanks, Paul.
So the unbalance, in order to answer that, we have to open maybe a case or the spectrum, but an unbalance would be usually a one-time peak on the line. On the side bands of the line frequency. The misalignment would repeat itself at multiple harmonics. So that's how you would separate the unbalance from a misalignment issue.
Okay, good. Any more last second questions? Anybody? All right. We'll let Tumay get home. I know it's late.
That's all right.
Thanks again for everybody, giving up their time and listening to our presentation. I hope you learned a bit, and hopefully we would like to hear from you in the future. And again, look for that next webinar in early December for Shoreline, showing the AMT Pro. But Artesis also does several of their own webinars, so make sure you check them out on LinkedIn and follow both companies. And we look forward to seeing you again. Thanks. Take care, everyone.
Thanks, Dan.